Welcome to Lecture B18, our next to last lecture of the semester. In this lecture, we will talk about confidence intervals, and we will learn how to do three different kinds of problems with confidence intervals. So let's start with the first type, and an example that the example that we want to consider is problem 25.3.4, which says determine a 95% confidence interval for the mean mu of a normal population with variance sigma squared equals 16 using a sample size 200 with mean (74.81). Now, in this lecture, we're going to look at a number of different tables pertaining to these problems that we'll be discussing. And just as was the case with the earlier tables that we discussed in previous lectures, so it will be the case with this lecture that if on the final exam there are any problems in which you need a table, that table will be provided. So let's look at this problem. We want to calculate the confidence interval for the mean in a problem where the variance is known and the mean is known. So if you look in your textbook on page 1069, you see table 25.1, which says confidence interval for mu, that's the mean, of a normal distribution with known sigma squared, with known variance. And that's the situation we have here. We have a known variance, and so the steps that we're going to follow to solve this problem are given right here. Now, the first step is to choose a confidence level, gamma, which is 95%, 99%, or whatever. And as we already said, the statement of the problem said to determine a 95% confidence interval. So for this problem, gamma is equal to 95%. Now, so that's easy. Now we go to step 2, determine the corresponding C. Well, since gamma is equal to 0.95, C is 1.96. So we'll come here and we'll say since gamma is equal to 0.95, C is 1.96. Now we go to step 3, compute the mean of the sample, and we're already told that the mean in this case is 74.81. That was given to us in the statement of the problem. right here, mean is 74.81. So we can just write down X bar is 74.81. And then the fourth step is to compute K, which is defined as being equal to C sigma divided by the square root of n. C sigma divided by the square root of n. So K is equal to C sigma over the square root of n. C is 1.96, as we've already noted right here. Sigma is the square root of the variance, and since the variance is 16, sigma will be equal to 4. And n is the number of samples, which is 200, so this will be the square root of 200 in the bottom. And K will end up being 0.55, and so we report our answer then in the following way. The confidence interval with the 0.95 means it's the 95% confidence interval, and the numbers that we will have here will be X bar minus K less than or equal to mu less than or equal to X bar plus K. And so when we stick in for X bar and we stick in this value for K, we get the final answer that the 95% confidence level or confidence interval is 74.26 less than or equal to mu less than or equal to 75.36. And that's how we calculate a confidence interval in a problem with a known variance. And that is the confidence interval for mu, for the mean. That's how we calculate that in a problem with a known variance. So very straightforward. You just need to understand how to use this table 25.1. And again, if you have a problem like this in the final exam, this table will be made available to you. Now, let's look at a different problem. The next problem will be 25.3.10. And in this problem, we want to do the following. It says find a 99% confidence interval for the mean of a normal population from the sample and this is in problem 10 is supposed to be dealing with the melting point in degrees centigrade of aluminum, and the samples are 660, 667, 654, 663, and 662. Now notice that in this case, unlike in the previous problem, where the variance sigma squared was given, in this problem, sigma squared is not given. So if we come back to our table, this table that gives us the confidence interval for mu with known sigma squared, this won't be appropriate. Instead, we need to go to table 25.2, and that table is in this same. Okay, let's see here if I can do this. I think I might be making things. Well, no, maybe not. Let's see. In making this copy, I apparently cut off the page number, so let me look for a moment and I can find the page number for you for this table 25.2. That is on page 1071 in your book. And as the words here indicate, determination of the confidence interval for the mean of a normal distribution with unknown variance sigma squared. So we have a different procedure for this kind of problem, and let's see how this goes. So it starts out just like the previous one. Choose a confidence level gamma, 95%, 99%, or the like. And you might recall that in this problem, they said a 99% confidence interval. So in this case, gamma is equal to 0.99. Now let's go back to the table. The next step is to determine the solution C of the equation f of c equals 1/2 of 1 plus gamma. And to do this, we're going to use table A9 in Appendix 5. Well, first of all, let's look at this equation. F of c is 1/2 of 1 plus gamma. So let's write that down. F of c is equal to 1/2 of 1 plus gamma. So this is 1/2 of 1 plus 0.99, and therefore f of c is 0.995. And now we want to look at some table to find out what C satisfies that. And the table that they've told us to look at is this table of the T distribution. Now you can see these values of f of z given. We have 0.995, but what column do we need to look in? Well, the column depends on the number of degrees of freedom. And how is the number of degrees of freedom defined? It's equal to n minus 1, where n is the number of samples. So let's go back and remind ourselves here. Okay, the samples that we have in this problem are 660, 667, 654, 663, and 662. So we have 1, 2, 3, 4, 5 samples. N is equal to 5. And so, of course, then n minus 1 is equal to 4. So we come back to the table, and we're going to look at, in the f of z column, we want 0.995, and for the number of degrees of freedom, we want 4. And so we're right here at 4.6. That is the value of C, or in this case Z. That is the value of Z that makes f of Z equal to 0.995 when the number of degrees of freedom is 4. So, but we're calling it C here, so C is 4.6. C is equal to 4.6. Okay, now let's return to the table A2 to see the next step. Okay, so again, we've just completed step 2, where we looked at table A9 to find the C that satisfied this equation. And now step 3 is to compute the mean x bar and the variance s squared of the sample. Okay, now the mean of this sample, x bar, is simply going to be 660 plus 667 plus 654 plus 663 plus 662 over 5. And if you wish, we can put K there in the top, because all of those were, oh, not K, but C, I guess, degrees C. And so x bar, if you do this calculation, you will find that x bar is equal to 661.2 degrees C. And now what about s squared? Well, s squared is equal to 1 over n minus 1 times the sum over j of xj minus x bar squared. So in this case, we get 1 over n minus 1, that will be 1 over 4, times 660 minus 661.2 squared. And I'll just hold the degrees centigrade squared till the end. So we have that plus 667 minus 661.2 squared plus 654 minus 661.2 squared plus 663 minus 661.2 squared plus 662 minus 661.2 squared. And as I said, the units, since all of those are squared, the units will be degrees centigrade squared. And if you do this calculation, you will find out that s squared is 22.7 degrees centigrade squared, which means that s is equal to 4.76 degrees centigrade. Now, we have done what was requested. Recall, we are now doing this step 3, which was to determine x bar and s squared for the sample. We have now found both of those, and the final step is to compute k, which is equal to cs divided by the square root of n. cs divided by the square root of n. So we come back here, k is equal to cs divided by the square root of n. C, recall, we found it is up here. C is 4.6. So we have 4.6. S is 4.76 degrees centigrade. And in the bottom we have the square root of n. Again, n was 5. So we have square root of 5. And when you do this calculation, you will get k is equal to 9.8 degrees centigrade. And therefore, the confidence, in this case, 99% confidence interval for the mean. We will have x bar minus k less than or equal to mu less than or equal to x bar plus k, and that turns out to be 651.4 degrees centigrade less than or equal to mu less than or equal to 671.0 degrees K. And that completes problem 25.3.10. So that shows you how you calculate the confidence interval for the mean of a normal population when the variance is not known. And now we want to do one final kind of problem in this lecture, and that is calculating a confidence interval for the variance. So as an example, let's look at problem 25.3.15. And this one says the mean energy in kilo electron volts of delayed neutron group for uranium U-235 fission I'm sorry, I've left off part of this problem. So here 25.3.15, we're supposed to find a 95% confidence interval for the variance of a normal population from the sample. And then in this particular problem, they're talking about the mean energy of delayed neutron group for uranium U-235 fission. And the sample, what the information we have about the sample is the following. It says a sample of 100 values with mean 442.5 Wait, I've want to stop this for just one moment because I think I've... Oh, no, this is great. Okay. Okay, with mean 442.5 and variance 9.3. And as you will see as we do this problem, that mean is not really important. We don't need to know that. It will not figure into our calculation. But the thing that's different, I want to stress the thing that's different about this problem from the previous ones we've done is that here we are calculating a confidence interval not for the mean, but for the variance. So now we go back again, and now we'll learn how to use Table 25.3, determination of a confidence interval for the variance sigma squared of a normal distribution whose mean need not be known. As we mentioned just a moment ago, the mean doesn't figure into the calculation. So as was the case with the previous tables, the first step is to choose the confidence level, the value for gamma. And in this case, we want a 95% confidence interval, so gamma is equal to 0.95. Now returning to the table, this is similar to what we did in table 25.2. Determine solutions C1 and C2 of these equations. Here f of C1 is 1/2 of 1 minus gamma, f of C2 is 1/2 of 1 plus gamma, and we're going to use a different table this time. We'll use table A10 and the chi-square distribution. And once again, the number of degrees of freedom is n minus 1, where n is the number of samples. So let's come back and we'll say f of C1 is 1/2 of 1 minus gamma, and f of C2 is 1/2 of 1 plus gamma. And this will give you f of C1 is 0.025, and f of C2 is 0.975. We get those numbers simply by plugging in this gamma of 0.95 and then doing the arithmetic. Now, in order to use this table, let's glance at the table again. They want us to use table A10 and appendix 5. And that table is shown right here, table A10 and appendix 5. And you see we have f of z. And for the two values given, remember we had f of C1 is 0.025, and so that's good. That's given right here. And f of C1 was 0.975, and that's also given. But we need to know which column to look in, which corresponds to the number of degrees of freedom. And remember, that's equal to n minus 1. Now, we were told again here that we have a sample of 100 values. So if we have 100 values in the sample, then n is 100. So we'll note that here at the top, n equals 100. So n minus 1 is 99. Now if we go back to that table we were just looking at, number of degrees of freedom equal to 99, well, let's go down here to the bottom of the table, and you see that actually we don't have an entry for that. We have a number of degrees of freedom is 90, and number of degrees of freedom is 100, and number of degrees of freedom is more than 100. Well, since 99 is as closest to 100, we'll use the values in this column for 100 degrees of freedom. Now again, f of C1 was 0.025, and so we come over and we'll have C1 is 74.2. C1 equals 74.2. And on the other hand, f of C2 was 0.975, and if we trace that over here to the 100 degrees of freedom column, we'll get C2 is 129.6. C2 equals 129.6. So now going back to table 25.3, okay, we have found C1 and C2, so we have completed step 2. And now step 3 says to compute n minus 1 times s squared, where s squared is the variance of the sample. N minus 1 times s squared. Okay, well, let's do that. N minus 1 times s squared will be equal to, okay, again, 100, n is equal to 100, so we have 100 minus 1, and s squared, well, we're given that the sample variance is 9.3. And so if we do this calculation, then n minus 1 times s squared will be 920.7. And that completes step 3. Now in the final step, we want to compute K1 and K2. K1 will be this n minus 1 times s squared that we just calculated divided by C1, and K2 will be that same quantity divided by C2. So K1 will be 920.7 divided by C1, 74.2, and K2 will be 920.7 divided by C2, which is 129.6. So we get K1 is equal to 12.41, and K2 is 7.10. And now to finish the problem, the confidence interval is K2 less than or equal to sigma squared less than or equal to K1. So our final conclusion is that the confidence interval, and remember in this case it was gamma is equal to 0.95, so the 95% confidence interval for sigma squared, the variance, is 7.10 less than or equal to sigma squared less than or equal to 12.41. And that's how we do a problem of that type. And so that those are the 3 kinds of problems that we wanted to learn about in lecture B18. And now let's look at some problems related to these examples. Okay, so the problems for this lecture are the following. The first one, B18.1, which is very closely related to problem 25.3.5 in your text, says what sample size would be needed for obtaining a 95% confidence interval of length 2 sigma. And one warning about this problem: when you do it, you will not come up with an integer. You will come up with a decimal number, but of course the sample size must be an integer. It must be a positive integer or a certain number of samples, and so just round your answer to the nearest integer, and the choices are A is 2, B is 4, C is 3, and D is 5. For problem B 18.2, for this one you should refer to problem 25.3.9 in your text. And it says find a 99% confidence interval for the mean of a normal population from this sample. And we have copper content in percent of brass. And the sample is 66, 66, 65, 64, 66, 67, 64, 65, 63, 64. All of those are the copper content in percent of brass. And so, therefore, I didn't put percent in all of these, but you should understand. Maybe I'll go ahead and put it real quickly. So this is percent, 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 and percent, and percent here. So the answers you have here, notice I won't keep on saying confidence interval, 99% confidence interval, because it's clearly that's what we want. And you see we have 99% confidence interval denoted on each one of your choices, A, B, C, and D. So what are the intervals? In A, it's 63.72% is less than or equal to mu is less than or equal to 66.28%. In B, it is 64.49% is less than or equal to mu is less than or equal to 65.51%. In C, it is 60.19% is less than or equal to mu is less than or equal to 63.74%. And finally, in D, it is 64% less than or equal to mu less than or equal to 66%. And finally, for problem B 18.3, in this one we want to find a 95% confidence interval for the variance of a normal population from the sample. And this is like problem 25.3.13. The sample is length of 20 bolts. So 20 is your sample size here. You have 20 bolts with a sample mean 20.2 centimeters and sample variance 0.04 centimeters squared. And so the answers in each case now, this is the 95% confidence interval for sigma squared. So each one of these should be sigma squared because it's a confidence interval for the variance. And the choices now are A, 0.23, 0.023 centimeters squared is less than or equal to sigma squared is less than or equal to 0.085 centimeters squared. 0.1 centimeters squared is less than or equal to sigma squared is less than or equal to 0.3 centimeters squared. That's B. C is 0.03 centimeters squared less than or equal to sigma squared less than or equal to 0.05 centimeters squared. And finally, D is 0.02 centimeters squared less than or equal to sigma squared less than or equal to 0.06 centimeters squared. And so that concludes all of the problems for this lecture, and therefore that's the end of lecture B18. Of course, as usual, we'll have other problems in class. So that's the end, and good luck.